This is Dr. Jaikanth Yadav, working as assistant professor in the Department of Mathematics at Institute of Aeronautical Engineering College. And my course title is Complex Analysis and Special Functions. Today's topic is Cauchy Integral Theorem. Yes, Cauchy Integral Theorem. Before we are going to discuss the theorem, we have some definitions here. So, a closed curve is called simple closed curve. We have a closed curve. That closed curve we call as simple closed curve if it does not crosses itself. Okay. So, for example, there is a curve which is like this. Here, this curve, the orientation is we are taking in the counterclockwise direction. This is our curve C. Counterclockwise direction. That's why the movement is like this. So this curve is does not intersecting, that does not crossing itself. That's why it is called simple closed curve. Simple closed curve. Okay, and if we see a second definition, a curve which crosses itself is called multiple connected curve. So if you draw a curve which crosses itself, in that case, that curve we call as multiple connected curve. For example, if yes, here the orientation is, I'm taking here orientation is anti-clockwise direction, and this here is this. Okay, here this curve is crossing itself. This curve is crossing itself. That's why I'm going to call this curve is multiple connected curve. Now, briefly, a curve is said to be simple curve if it does not crosses itself. Next, a curve is said to be multiple connected if it crosses itself. In that case, we call that curve is multiple connected curve. Next definition is simply connected. A region is said to be simply connected if every closed curve in the region encloses points of the region only. Okay, suppose we have a region. That region is bounded by some. This region. This is region R. In this region, I am going to take a closed curve. Every closed curve in the region, if I am taking a closed curve in this manner, so it is crossing. Yes, so there is a curve. This is the curve, and I have this region is there. This region is said to be simply connected. When if I am going to take any closed curve, every closed curve in the region encloses all the points, encloses the points of the region only. See, I am taking this curve. This is a closed curve in the same region. And what this curve is doing? This curve is encloses the points of the existing region only. So that's why we can call this region is simply connected. Simply connected region. This region. I am taking any closed curve in this region. That closed curve encloses the points of this region only. Hence, we call this curve is, this region is simply connected region. For example, if I take another region, there is one circular path, and I am taking another circular path, and my region is this. It's an angular region. We call it as angular region. Okay. Now, this region is simply connected region or not? Okay. In this region, if you take some closed path, I am taking this is the closed path. This closed path encloses some of the points which are not belongs to in the circular region. Does not belong to the angular region. Here, my region is angular region, and I am taking in the angular region, I am taking a closed path. This closed path not containing, there are some points which are not been, this is covering some of the points. There are some points which are not belongs to the angular region. So that's why this angular region is not simply connected region. It's not simply connected region. So here you see definition for a region which is not simply connected region. That region we call as multiply connected region. Okay, now here we learn the definitions of simply closed curve, multiple connected curve, and simply connected region and multiply connected region. Now there is a statement of Cauchy Integral Theorem. For this theorem, we need a function f z is analytic. Function must be analytic, and derivative of f means f prime of z. It should be continuous at each point within and on a simple closed curve. Simple closed curve. Then we can have integration along C fz dz becomes 0. Right? Once again, if the function is analytic and the derivative of f is continuous, this is where these two are satisfied within and on the simple closed curve C. In that case, integration along closed curve C of fz dz becomes 0. Okay. So here there is a sufficient condition for an analytic function whose integral along the closed path is 0 is that the function fz should be analytic within and on the closed curve C. In that case, the integral will be 0. This is the theorem statement, and here we can see there is a corollary. If fz is analytic in a region or in some region or fz is analytic, and there are 2 points P and Q are 2 points in the region R, then integration from P to Q fz dz is independent of path joining P and Q and lying entirely in R. For example, there is some region, this is my region R, and here in this region fz is analytic. Okay, now we are taking any 2 points in this region here I am taking this is point P and this point as Q. So I am performing integration from P to Q. So when we are going to perform integration, we need a path. So here I have another one path, that is C1. So we are performing integration from P to Q along C1. This integral value and integration, and there is another path which is C2 path. C2 path, and we are performing integration from P to Q only. Here, because these two paths are lies in the where fz is analytic. So that's why here integral is not different. Integrals are same because the function is analytic in this region. That's why the integral is independent of paths. We take any path joining P and Q, integral value will be same. Okay. Now we have to remember one is that a function fz is fails to be analytic at a point z0, but in every neighborhood of z0 there exists at least one point where the function is analytic. Then z0 is said to be singular point, or z0 is called singularity of f of z. So this we discussed when we discussed analytic functions. So here we define a singular point. So a singular point is a point which is fails to be analytic, and every neighborhood of that singular point, there should be at least one point where fz must be analytic. That point we call as singular point. Here we are taking z0. At z0, function is failed to be analytic, but we are finding some other point in every neighborhood of z0. We are finding some other point which is at which the function fz will be analytic. Okay, so there is singular point. For example, if you take f of z is 1 upon z. Here we know derivative of z. Derivative of z is minus 1 upon z square. This derivative is not exist. When it is not exist, because derivative function is rational function, denominator is z square. If the denominator becomes 0, you make it z square and the denominator equals to 0, you will have z value is 0. So at z is equal to 0, denominator will be 0. Whenever denominator is 0, at that point, function is not exist. Means derivative is not exist. So at z is equal to 0, derivative is not existing. It means what? Z is equal to 0 is z is equal to 0, function is fails to be analytic. But in the neighborhood of z is equal to 0, we can find at least one point where function should be analytic. Okay, that point we can find in every neighborhood of z is equal to 0. We can find a point function to be analytic. Hence, z equal to 0 is a this is x-axis and this is y. Z is equal to 0 is singular point for f of z is equals to 1 by z. Now, example 2. What is singular point of f of z is equals to 1 by z minus 2. So we know derivative of this function is minus 1 by z minus 2 whole square. This implies if you, because it is a rational function, denominator equating to 0, you will get z is equal to 2. So z equal to 2, and other than 2, all the points will be, other than only 2 fails to be analytic. Remaining all points are satisfying the analytic condition. So that's why in every neighborhood of 2 we can find at least one point where functions to be analytic. So that's why 2 is a singular point. In this way we can find a singular point for different functions. Okay. Now here you can see evaluate the integral over c z square plus 3z plus 5 dz. Okay. Here the curve c is a circle and defined as mod z is equals to 1, oriented in the counterclockwise direction. So first of all, you try to draw the diagram of this curve. Here I am taking complex plane. In the complex plane, horizontal axis denoted by x, vertical axis denoted by y. So this is mod z is equals to 1. Mod z is equals to 1. Here c is mod z is equals to 1. Is a circle. It is a circle whose center at 0. I am writing it. Mod z minus 0 is equals to 1. So z is equal to 0 is the center of the circle whose radius is 1. This is simply mod z is 1, and this is z is equal to 0, and the radius is 1 unit. Okay, so we need to perform integration along this circular path. When we are going to perform integration along this circular path, what we are taking, parametric form we are taking here. But here one thing we can observe. Here f of z is z square plus 3z plus 2 plus 5 plus 5, which is a polynomial. You can observe this, which is polynomial in z. We know every polynomial is analytic in the whole complex plane. On whole complex plane. So f of z is also analytic. So z is equal to, mod z is equal to 1 is a subset of the whole complex plane, right? So mod z is also analytic within and on the curve C, on the closed curve C. We know the curve C is a simply closed curve because it is not intersecting, it is not crossing itself. That's why it is a simple closed curve. And our function is within and on the boundary, it is analytic by Cauchy Integral Theorem. We have integral fz dz along the closed path C is equals to 0. Here we know here f of z is what? Z square plus 3z plus 5, and C is, we know, which is mod z is equals to 1. C dz, this is 0. So we are getting this conclusion with the help of Cauchy's integral theorem, because our integrand is analytic within and on the boundary of C. Okay, that's why we are getting result is 0. So because function is analytic in the simple closed curve, evaluation of integral is very simple. Next, we'll take another example. Here, let f of z taken as e power z by z minus 2. Here, what is curve C? Curve C is mod z is equals to 1. Draw the diagram. Complex plane. In complex plane, horizontal axis and the vertical axis. And this curve C is say unit circle of radius 1, center at 0. So center at 0, this, and here this is our curve C. Mathematically it is mod z is equals to 1, and the radius is 1, and this is the center, z is equals to 0. Clear? Right. So is it a simple closed curve or not? This is simply closed curve. Okay. And here, now, what is f prime of z? We calculate what is, because I want to find the singular points of the given function. Singular points of this function will have denominator will be firstly denominator z minus 2 whole square, and keep denominator side and perform derivative for the numerator, which is e power z only, minus e power z keep aside and perform derivative for z minus 2, you will get 1. And now you will have it is z minus 3 e power z by z minus 2 whole square. So derivative function got rational function. So I want to find where derivative is not exist. So in this case, I have to take denominator of the rational function equating to 0, so that I can find where it is not exist. F dash of z where it is not exist. So for singular point, I am going to equating denominator to be 0. That means z minus 2 whole square equals to 0. This implies z is equals to 2. So therefore, z is equals to 2 is singular point. So here within the given circle, there is no singular point. If there is no singular point, it means that the function is analytic within the unit circle, and z is equal to 2 somewhere outside the circle. We have z is equal to 2. Z equal to 2 lies on x-axis somewhere. This is z is equal to 2. Here our function f of z is analytic. So singular point is there outside the given circle. So I will write here f of z is analytic. Take inside, within, and on the curve C. Curve C. What is C? C curve is mod z is equals to 1 by Cauchy's theorem. Cauchy's integral theorem. We have integral of f of z dz over the closed curve C, simple closed curve C is 0. That is, in this problem, integral along C, here f of z is exponential z by z minus 2 dz is equals to 0. So, here it is easy for us. In the case of function is analytic in the simple closed curve, then we can directly write integral value is 0. Similarly, third problem, if you see here, what is integrand? F of z. In this problem, integrand is x square minus y square plus 2ixy. This we can write in terms of z. That is my interest. So I want to write in terms of z. We know z is x plus iy. So for that, I want to write it is a function of z. So that's why it is x square plus I y whole square plus 2xiy. This can be written x plus iy whole square. That is z square. See, we have to evaluate this term. Here, integration along the curve C. C is the unit circle centered at 0. And now we have the function is f of z is z square. So, and C is mod z is equals to 1, or it is a circle. The center is 0 and radius is 1. Is a simple closed curve. We know f of z is equal to z square is polynomial function, and it is analytic. So within and on the curve C by which theorem? Cauchy's integral theorem. Integral theorem, we have integration along C, fz dz is 0, or we know here f of z is x square minus y square plus 2ixy dz. Here integration along closed curve, so that's why we are taking circle on the integral symbol over C. This value is 0. So here, because the integrand is analytic within and on the closed curve C. Okay. So these are the references for this lecture, and for this course also these books are very helpful. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.